Oh, hi, Ata. How are you?
I'm fine, hocam. Thank you. How about you?
Good. Nice to see you.
Yeah, you too.
Okay. So I guess we are on time. We can start with your presentation now.
Okay. Okay. Hello, everyone. So I hope you are having a great workshop, and we are not even halfway through. So now in this section of the workshop, we'll go through some horizontal axis wind turbine rotor CFD simulations using SU2. So I divided this presentation into three parts. First, we'll go through some wind turbine rotor aerodynamics and how we can implement this phenomena we see in rotor aerodynamics into CFD simulations. And then, although as Gorbay has already went through the capabilities of SU10 tutorial, I want to focus on the settings related to wind turbine rotor simulation. So we'll go through with that. And then at the end, we'll do an application, a test case at the end of this presentation. So for a modern horizontal axis wind turbine, we see commercial operating in both onshore and offshore. We see tip Mach number around zero point 0.2. So we still have incompressibility assumption valid on the wind turbine blades, but we may also have compressibility depending on the case. So as you might already know that if we exceed Mach number about zero point 0.3, then the incompressibility assumption becomes invalid. So before running a CFD simulation, you may want to check that if your case is suitable to do an incompressible simulation. Also, in terms of angle of attack, as you can see in the figure on the right-hand side, we have very high angles of attack exceeding the stall angle near the root. But at the mid and tip sections, we are still in the linear regime in the airfoil polars. So you may also want to take this variation angle of attack into account. So in terms of Reynolds number, so usually we are in the order of 1 million or 10 million of the Reynolds number of the flow on the blade. So for such a high Reynolds number, we need a high resolution requirement to model the turbulence in the flow. So you have to generate your mesh according to this resolution requirement. So in a few slides back, I mentioned about the high angle of attack near the root. So we have this high angle of attack, and also we have very thick airfoils near the root. So this combination usually leads to the flow separation near the root. And it's a bit difficult to model flow separation with conventional Rand solver. If you want to get a really good result on the separated region, you may need some higher order methods, or you need a very good mesh resolution to capture this separation well in the root region. In addition, we may also see some transition from laminar flow to turbulent flow. So for small wind turbines, we may still see this laminar flow on the blade affecting the turbine performance. And the computing determining this transition point is quite crucial on the performance calculations. But for large commercial wind turbines, we usually see fully turbulent flow. I mean, in other words, a transition points almost at the leading edge, not affecting the performance of the turbine. And also, this is due to high Reynolds numbers. And also, in reality, we have leading edge contamination on wind turbine blades. This also promotes turbulent flow quite early compared to an ideal case. Uh, so we have the blades as the aerodynamic surface of our wind turbine. We also have additional components like the spinner connecting just ahead of the turbine blades connecting them. We have the nacelle downstream, usually downstream, and also we have the tower. And right, you can see the results, the CFD simulation results on the right-hand side. So at the top, we have only blades. We have this quite good symmetrical wake profile. And also we have this jet in the center due to the lack of any components there, like the spinner or nacelle. But if we include these components, like you can see on the top figures, we have this asymmetrical wake profile, mostly due to that tower wake, tower shadow, as you can see. Horatio, just let me open my laser pointer. Yeah, over here you can see that this promotes this asymmetrical wake profile, and also we see that the jet in the center disappears due to the presence of the nacelle. And also, in addition, the diffusion characteristic of the wake is quite different when we include these turbine components. So depending on your application, you may need to include these components in your mesh. But literature also shows us that we can have similar velocity profiles over the blade, even without these components. And just getting rid of these components will save you a lot of computational time. So if you want to just see the turbine performance, the blade performance of your design or your flow control approach, you can just simply model the blades without any components and do the simulation. But if you want to look into the wake of the turbine, or if you want to put some additional turbines downstream, then you may need these components modeled. And the environment wind turbines operate at are quite complex. We don't just have the turbine itself. We can just isolate it. So in terms of an onshore wind turbine, we also have the ground. And if we have a complex terrain, then the wind profile will be affected greatly due to this terrain, and this would affect the wind farm placement. For the offshore turbines, we have the sea, and we usually have the waves on the sea, which affecting the results. And also, if you're also simulating a floating offshore wind turbine, then also you have to consider the movement of the turbine due to the waves on the sea. So you may need to couple your flow solver with an hydrodynamic solver, and also you may need to solve the motion of the wind turbine as well. Also, in reality, we don't have uniform flow incoming to the wind turbine. We usually have an atmospheric boundary layer or a wind shear. So this is, as Professor Cesaruzzo mentioned on his presentation, we have a non-uniform velocity profile, and we need to force them into our inlet boundary in our CFD if you want to model this atmospheric boundary layer. It affects both the incoming flow velocity and the turbulence, as you can see from the figures on the right-hand side. As we add wind shear on the inlet, then we see some differences in the wake profile compared to the uniform inflow case here. But if we have a wind turbine outside of the atmospheric boundary, like a very large wind turbine or an airborne wind energy device, then we may not need this atmospheric boundary layer, but in most cases, we should. Wakes are an important aspect of wind turbine simulations. It is we have reduced velocity and increased turbulence downstream of the turbines due to the rotational movement of the turbine blades, and also the interactions with other non-rotating elements of the turbine. Also, the wakes also affects the wind turbine performance as well, and we have these tip vortices emerging from the tip of the wind turbine blade. So you may need a very high resolution mesh around here to accurately model your tip vortices. And also the wakes and also the performance of the wind turbine are affected by the wind turbine control, as you can see the case over here, as we include a yaw control to our wind turbines, then we see differences in our turbine power coefficient and also in the wake. So this is the same case. So we have this yaw alignment for the upstream turbine, which affects the wakes downstream. And at the end, we may have this partial alignment with our downstream turbine. So we need a very good modeling for this region to get an accurate wake shape for the valid performance calculations for our downstream turbine in our CFD simulations. We can also consider some additional elements like the surface roughness. So we have leading edge contamination and erosion usually on commercial wind turbines. It reduces the turbine performance, and in your CFD you may either directly model it through your mesh by simply modifying your airfoil surface, blade element surface, or you may use roughness models to model this surface roughness. Also, the wind farm control is a very hot topic in the wind energy community. So people are trying to develop these novel methods to increase the overall power output from a wind farm. But this affects the rates of your turbine, which requires a very good modeling. So you may need some high fidelity CFD simulations to accurately model to accurately assess the power output from each control approaches. And lastly, for this section, gusts are also important aspects of wind turbines. So it's a brief increase in the speed of the wind. It may reduce the effectiveness of the wind turbine, but more importantly, it affects the structural properties of your turbine. And since you have this sudden high speed, high speed wind, then it is practically impossible to adjust your wind turbine pitch or rotation speed immediately from this wake. So this would affect the structural properties. So you may need some fluid structure interaction simulations if you want to get onto with this gust phenomena. Okay, so now let's talk about the SU2 capabilities and just follow some tutorials on rotor simulations. So SU2, I think it's a very quite an easy to use software. So the only thing you need is a simple text file, including all the settings for your configuration. So in your terminal, you just need to enter these commands, the executable SU2 CFD, and the name of your configuration file. And if you want to do a parallel simulation in a cluster or on your own PC, you need to put this MPI run, specified number of cores, and again, the executable and the configuration file, name of the configuration file. So I won't go over the whole cases, the whole configuration files, but on this GitHub link, so just let me share you this screen. So over here. So you have this GitHub page for the SU2, and on this page we have this template configuration file. So if you want to look into this template file in more detail, you may enter this, you may get into this web page, and you'll have all the possible options for an SU2 simulation over here, as you can see. You have the link in this presentations. You may want to check this link on your own free time after the workshop. So SU2 uses in simulations, SU2 uses two loops. One is an outer time loop, marching through the physical time at each time step, and an inner loop, which is usually a pseudo time iteration loop. So if you are doing a steady simulation, by disabling the time domain option, you just only need the inner time loop, and you specify the number of iteration with this iter option. But if you'll do an unsteady simulations like a rotating wind turbine rotor, then you need to enable this time domain option and specify some parameters related to the simulation, like the physical time step in seconds, the maximum time the simulation will run in seconds, the number of inner loop iterations, and the number of time iterations. So the simulation time is determined by the minimum of the maximum time and the multiplication of the time step and the number of time iterations. Boundary conditions are quite an important aspect of your simulation. So in SU2, you specify the boundary conditions with a set of settings starting with this marker keyword. So for a constant heat flux or for a no-slip condition, you can use this marker heat flux. You may specify a constant heat flux for your surface for a boundary condition, or you can use an adiabatic wall, which is the mostly used, conventionally used option for the wind turbine blades or other components. So this name comes from your mesh. So while you are preparing your mesh, you have to specify a name for your surface in 3D. So in 2D, it's lines, in 3D, it's surface. And you use that name in your SU2 configuration file. You can also use the far field boundary condition where the free stream values are enforced. So this is marker far. And you can use this boundary condition even on the inlet or on the outlet or on the side surfaces. It depends on your application. For the outlets, you can give the back pressure or the mass flow target. So for the mass flow target is you to adjust the pressure boundary condition on the surface to match this mass flow target. But also for the outlet, you may also use the far field boundary condition as well. So inlet is a bit more important than the outlet because as I mentioned earlier, we may have a wind shear. So first, you need to define the inlet type. It could be total conditions, mass flow, or incompressible velocity or incompressible pressure. Then you should specify the marker inlet, the name of the boundary condition surface, total temperature, total pressure, or density, velocity, magnitude, or in terms of incompressible, just the velocity, magnitude, or the pressure, and then the flow direction. So you have to specify this one, even if you want to give a non-uniform velocity profile. Then, for a non-uniform net profile, you need to enable this specified inlet profile setting. Then, SU2 will search for this inlet file in your directory. If SU2 cannot find such a file, then it will generate a template in that file, which contains the nodes for the marker you specified in this marker inlet option and the required variables. And it will just put the variables you put here. So even for a non-uniform net profile, you need to specify some numbers, some arbitrary numbers is fine. And then by manually, you can just adjust these values. And then again, put your modified inlet file and then rerun the simulation. And in this time, you'll have a non-uniform inlet profile. Periodic boundary condition can be used in wind turbine blade simulations as well. So if you remember from back, if we only have this blade, and also if we have some symmetrical components like a cylindrical nacelle or the spinner, then you may just use a part of your configuration to save up some computational time. Like let's say we have a 3-bladed turbine. You can just get a single blade and 120 degrees part of your nacelle and spinner if they are in your simulation. Then assign some periodic boundary conditions on the sideways, and then you can do your simulation. And you need to specify this marker periodic boundary condition. You need two separate surfaces. You need to specify the rotation center, which is usually the origin. You need to specify the rotation angle. So for an wind coming from the x-axis, your rotation angle or periodic rotation angle will be on the x-axis. And for a 3-bladed turbine, it is 120 degrees. For a 2-bladed case, it's 180 degrees. And you usually do not need to specify any translation periodicity in wind turbine blade simulations. But the problem with periodic boundary condition is that you may not have a symmetrical wake in an accurate simulation. But in this case, by enforcing periodicity, you'll end up with this symmetrical wake profiles usually. So it depends on your application. So if you again need a very accurate wake velocity profile, wake distribution, maybe this is not good for you. But again, if you want to do a quick simulations of your blade, then this will save up a lot of computational time. Okay, we have this configuration file, but we need to post-process our simulations. So what to get in our output files? The website of SU2 has a very detailed list of outputs, but some of these outputs may not be suitable for your configuration file. To check which output fields you can get at the end of the simulations, you need to do a dry run with this command. So by putting this flag -d in your command, SU2 will start to check your configuration file to see if there's any error. And then at the end, it will list all the available output fields. So you can take the ones that you want to check at the end of your simulation and put it in your configuration file, and then remove this dry run flag and do the simulation. For the rotor application, these two are quite important. So you may put the rotating frame option in your history output field, which includes thrust and torque. And also you may need a vortex identification in your volume output field, which would include some important parameters like vorticity and Q criteria. So we have this rotating blades. So we need to put some rotation in our simulation. So to define the dynamic mesh, you have two options. One is a rigid motion. You physically rotate the whole mesh. The second option is a rotating frame. So you can do a steady simulation of a wind turbine rotor by adding source terms in your flow equation through this option. So in a rigid motion, it will be an unsteady simulation. In a rotating frame, for a rotating frame option, it can be a steady simulation. But the literature shows that using a rigid motion option is more accurate compared to rotating frame, but again, with a higher computational cost. So for both options, you need to define the Mach motion, which is used for initializing and computing the force coefficients. You need to specify the motion origin and the rotation rate. So this is in radian per second. So this is rotation around the x-axis, y-axis, and z-axis. So for a single blade without any components, you may rotate the whole grid, the whole domain without any problems. But if you want to include some non-rotating components like the ground or the tower or nacelle, then you need to specify different domains. And for each domain, you should have different configuration files. For the main configuration file, you have to enable the multi-zone option and specify the names of each sub-configuration files. In addition, you need to give the boundary contours, the surfaces at the interface of these subdomains, so that SU2 can interpolate the fluxes from one domain to the other. Again, you may specify the interpolation method with this option. So for the rotating part, you need to specify a grid movement type. It could be a rigid motion, it could be a reference frame, and give the mesh file name for your inner domain, for the rotating domain. For the domain with the non-rotating components, you need to disable the grid movement option and give the name of the mesh file. So these are the additional things I mentioned earlier. So you may use a wall function if you have a very high y plus distribution, which is not good for simulating the boundary layer on your surface. So you may need to put some wall functions to increase the accuracy of your boundary layer velocity profiles on your surface. You may use this wall roughness model in SU2 to model your roughness case. And also you may use this gust model to see the effects of gusts on the wind turbine blade. You can check these ones in more detail from that template configuration file I showed you earlier in this presentation. Okay, now let's look at some application. So in this application, I will use Gmesh for the mesh generation, as apparently SU2 for solving the flow, and also I briefly show some results with ParaView. But I will put emphasis on the things related to the wind turbine rotor, as in this workshop we already seen very detailed explanation of both all software for an airfoil case. So this is our wind turbine. It's a very simple design. It's a tubulated turbine with a rotor radius of 5 meters. It rotates at 72 revolutions per minute. We have this NRAS S826 airfoil. So for the whole case over here, we have a single airfoil profile, but we have different twists at root and the tip. We have the circles near the root and the interpolation between circle and airfoil over this region. We have a uniform inlet velocity, 5 meters per second, which corresponds to a tip speed ratio of 7.5. So the good thing of open source, with open source software, you can compile them on the cluster at your home directory. So I know that Truba has SU2 already compiled, but I don't know about Gmesh. You may want to check that later on. But it's always good to have the most updated version available in your cluster. So you can compile this both software in your home directory, which I did, and I will show you how to call them in your submission file, job submission file. So in the submission file, we will generate both the mesh and do the CFD simulation with the just single file. So just let me show you um, our job submission file. Just a moment, please. Yep. So let me share my screen. So this is a sample job submission file for our case. So if you are familiar with the job submission on Truba, so this is the command you need to submit your job. So you need your account name specified, the name of the job. You need to specify the partition and also the number of nodes and cores you require from the cluster, and also specify a runtime. You may also specify the names of text files where you can reach the output, screen output, and the error messages. And also you may put these two commands to get email alerts when your job has started or finished. So the thing about compiling your own code, you also need to specify the modules you used while compiling your code. So in this file, it's always good to store these modules you use while compiling your code in a separate text file. So so with that, you can call these modules with this source command, and this is just a text file including all these modules while I was compiling my codes. So with this comments, I became sure that I have the same versions of 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 compilers like the C compiler while I'm doing my job on Slurm on Truba, sorry. So with this comment, I call Gmesh. So this is the user home directory where I have the folder Gmesh, and I compiled the code on this build folder. I called the executable Gmesh, and I have the Gmesh script, the main script, the name of the script over here. I'll show you in a moment. And then I run SU2 in parallel, and I specify the name of the configuration file here as well. And at the end, I get some statistical information on my job, and then exit. So this is the overall view of our mesh. So I try to keep it as simple as possible. So we have a single blade, just a single blade with periodic boundaries on Z equal 0 plane. And when you run the G mesh, you'll end up with a mesh with around 200,000 cells and 20,000 surface cells. Now let's check the Gmesh script. So I showed you how to call the Gmesh with the main Gmesh script, and now let's look into that in more detail. So this is the main Gmesh script we called while we are running Gmesh. So we have all the input parameters. We have all the design parameters I showed you earlier in the slide. You may play with them, changing the design of the turbine quite easily. The design of the blade, sorry. So we have the node counts specified here. and then we include some additional Gmesh scripts. So this is for the airfoil coordinates and generating the airfoil surface. This is for the wind turbine blade geometry and the surface mesh. This is the inner domain, the domain close to the turbine blades. We have the outer domains over here. So as I mentioned earlier, we need to specify the names of our boundaries. So you can do that by this physical surface option for your 3D mesh. So for example, in this case, we define the names of period neck and period pos for our periodic surfaces on z equal to 0 plane. We also have far field boundary specified here and the inlet boundary. Then with the volume option, we define the 3D volumes. So these are the values given to the surface loops. I will show that in a minute. So these are the volumes. With this option, we generate the 3D volumes, and these are the numbers given to the volumes, to the different domains. So I commented out this option, which would increase your cell count in your mesh. So with this one, you can dictate mesh sizes within a specific region. So for this case, we have a box with coordinates specified with these options xmin, xmax, and the other coordinates. Again, I specified these coordinates depending on the radius of your blade. And from here, you specify the mesh sizes outside the box and within the box. And by putting this option background field equal 1, 1 comes from this field, you enable the mesh sizes. And while generating the mesh, Gmesh will take this mesh size into account. Following, we define the mesh format. So 42 corresponds to SU2, but we have all different mesh formats. Similar to the boundaries, I also specified the volume as like a physical volume. So this is needed to get all the cells on your mesh file. If you do not include this one, Gmesh does, I don't know why, but Gmesh does not put all the cells in a mesh file for SU2 format. So if you if you disable the save all option as I did here, you will not have this marker, the volume, like a boundary condition in your mesh file. But in some cases, I saw that you may also have that option. So you may need to manually remove the marker, the volume. But on my, like when I generate the mesh with a single job on Truba, then I won't end up with this marker in my mesh file. But while I'm using the graphical user interface in my personal computer, I ended up with these markers, and I manually removed them every time. So you may want to check this one. You may want to check out better if this one is in your mesh file. So we can specify the mesh algorithm over here. So these are the options. You generate the mesh with this option mesh 3, remove any duplicate entities, and save your mesh in with this file. So now I want to show you a few things. I won't go over this whole files, but I just want to show you how to put boundary layers on the blades in this file, and also how to define periodic boundary conditions. Just give me a minute. This is blade, and this is the period. Okay. Let me check. Yeah. So this is the blade geo file. With this file, we can generate the turbine design and also get the mesh generate the mesh. So over here, you can generate the boundary layers by using this extrude option. You give the numbers of the surfaces, which are defined over here, as you can see here by this plane surface option, and then give the number of layers and the final thickness for your boundary layer cell. If I enable these ones, it will generate the boundary layers, and also you need to specify the surfaces of these boundary layers, as I did over here in your surface loop, which will be used to generate the mesh volume. And this is the script for the inner domain. So okay, over here, so we generate the surfaces. So this is the surface, I believe it's negative on negative y, and this is at the positive y at z equals 0 plane. So by specifying the numbers for each surfaces, we define the periodicity, and the periodicity is achieved by rotating this surface on the x-axis by minus p radian, which corresponds to 180 degrees. And with this option, Gmesh dictates periodicity on the surfaces. Okay, I think we are running out of time, so I'll quickly show you the SU2 configuration file. Again, just hang on, please, and then we'll quickly look into the results. There's this one option in ParaView I want to show to you. Yeah. So this is the configuration file. This will be shared later on after the workshop. Don't worry. You may play around with this one in your own time. So we have the time domain here, time marching method, and the time step. So this value corresponds to a 1 degree rotation of our turbine with for the specified rotational speed, which I gave earlier. So we have the uniform velocity, piston velocity, as you can see here. We have the marker heat flux for our blade, inlet boundary condition. Again, we specified uh, density and the velocity magnitude. We have the far field condition. You don't need to specify anything but the name. And we have the periodic boundary condition here. So we had the period neck, period pulse. These are name of the markers. The rotation is at the origin, and we have a 180-degree rotation on the x-axis. And we rotate the whole mesh with the rigid motion option for this radian per second on the x-axis. So it rotates counterclockwise. We specified the name of the surfaces we want to plot later on from the surface flow file. And these are the numerical methods. You can check them later on. So I specified the maximum time and the number of time iteration over here. And I have all these output fields over here. As you can see, I put the rotating frame option in the history output part, and I had the vortex identification in the volume output. So at the end, we'll end up with 4 main output files: the history file containing the variation of residuals, force coefficient, moment coefficients. We have the 3-dimensional flow file where we had the volume flow results. I like to use ParaView, so that's why it's in VTU format. We have the surface flow results and the force breakdown, which gives the force and moment breakdown by each surface specified. So you may specify the blade, you may specify like if you have the nacelle, and you can see the forces on the nacelle and the blade separately. So I'll share now. This will be the last thing, I promise. So now I'm going to show you the ParaView quickly. I just want to show you one filter specifically. So we have this domain. So it's simply a half of a cylinder containing only a single blade. So to complete it, we use the transform filter. Or here, let me show you. So we have the transform filter. It asks the periodicity and the periodicity information. So in our case, we have a 180-degree rotation on the x-axis, and with both fields enabled, we have the whole domain. So now let's look quickly to a slice on the y plane, y equal to 0 plane. Let's make it 2D, and we have our whole blade. So I have the results for each 10 time steps correspond to 10-degree rotation. So let's look at the animation, how the flow propagates downstream. So let's look at the axial velocity. I think I put no, okay. So, and then let's range over time. So this is the initial condition. And if I press this play button here, and then I have the rotation of the blades and the propagation of the wake. As you can see, we have this reduced velocity. And due to the lack of any component at the center, we have this jet, as you can see over here. And we can see the velocity reduction and also some increased difference in velocity at the tip as well. But of course, this is not quite a valid result. We need some improvements for get an accurate result. So we need to put some shorter first cell height for our boundary layer to lower the Y plus. If you cannot do that, if you cannot afford the computation time, you may put some wall functions. It's always possible. You may put a transition model. There are two available transition models in SU2 to capture the laminar flow and the transition point. You may want to model the remaining rotor components and non-rotor components, but in this case, you'll end up with a more complex mesh, and you need to specify different domains, like the subdomains in your SU2 configuration file. You may put the atmospheric boundary, but again, you cannot put an atmospheric boundary layer for a completely rotating mesh. You need to specify the rotating components and non-rotating parts separately. If you want to do a validation case for a numerical model, you may want to put some wind tunnel walls, which would increase the blockage, which would include some blockage effects on your wind turbine, which would affect the performance of your wind turbine. Lastly, but definitely not least, you may want to put some finer mesh around the blade and the wake region to accurately model this wake and some kind of a turbulent structure. Of course, it's not very possible to model this turbulent structure in a URANS or RANS solver, but still you may get some turbulent structures by putting finer mesh around the blade region. So this is the end of my time. If you have any questions, I think I can answer. I think we have some time. Let me check.
Thank you, Ata. There is one question. Is it possible to analyze twin rotor wind turbines in SU2?
Well, of course you can simulate them. All you need is just to have again two separate domains. You need to one domain containing this rotors and another domain for the other parts. It could be the tower, it could be the ground, it could be other things. And then you need to put different configuration files apart from the main one for these two things, and then specify the grid motion for the rotating file for the rotors, and for the other one, you disable the grid motion.
There's another question. Does SU2 have an incompressible solver? I mean, a true incompressible solver.
I'm not sure about that. I know that they use some
The equations, right? They use.
Yeah, but I'm not sure about that. The SU2 has a very good paper about their numerical methods. I can send you that later. They use a pressure correction factor as far as I know, but I'm not 100% sure.
Okay. Yeah, I couldn't remember right now, but I don't know if they have pressure velocity coupling simple methods. In the methods, yeah, you can check always the solver and the codes, also the documentation page. I'm not sure right now either. We most of the time, we mostly use the compressible flow solver, and it is more robust. I mean, you have full equations to solve. So, okay, thank you, Ata. I guess we are on time. Great. So we can continue with Hussein. Are you ready? Hello,
Hello
how are
everyone.
you?
Thanks,
Nice to
Hocam.
see you.
Nice to be here. Thanks for the invitation. I missed all of you.
Yeah,
Nice to be here.
I hope you are doing well in your new university. And
Yeah,
Ata also, Ata and Hussein graduated this summer, as I said before, so they are still contributing and working with us. So we are lucky to have you here.
thanks.
Um,
Thanks.
nice to see you. Okay, so you can share your presentation.
Okay, Can you see it?
Yes.
Okay.
Uh,
Hello,
before
everyone.
before starting, maybe there was one question about SU2. What is the scalability of SU2 on clusters? I mean, the computation wise. I mean, it's a finite volume solver. CFD solvers usually, I mean, the scalability after some, it depends on the grid size, mesh size, and after some point it goes linear, but then it diverges from the linear scalability as usual. So, but we can, I mean, it depends on the problem and the solver methods that you are using. You can easily check yourself as well, the performance, parallel performance. Okay, thank you. Thank you, Hüseyin. We can now listen to you.
Hocam, again, hello everyone. I'm Hüseyin. Greetings from Adana, and today my presentation will be about 2D simulation of a vertical wind axis turbine using moving reference frame technique in OpenFOAM. So I knew that all the previous presenters were going to talk about wind turbines, wind energy in detail. So I will focus mostly on the use of Truba server and a little bit to OpenFOAM, and I will do a hands-on demo, hopefully. So first, I will start briefly with wind turbines, vertical versus horizontal axis wind turbines, a comparison. And I will, in a single slide, talk about simulating rotating geometries in CFD. And then moving on to the method section, I will briefly talk about OpenFOAM and explain the moving reference frame technique, again, very briefly. Then we will move on to the demonstration. We will access the Truba server. I will present the details of our case study. I will show the OpenFOAM case structure, and finally we will move on to the simulation. And we will discuss the results and conclude finally. Okay, let's start with the introduction. As you know, wind turbines are mainly separated into two categories: horizontal axis and vertical axis wind turbines. Vertical axis turbines have some various types: Savonius, Darius, and H-rotor. If you compare them, you are going to see that horizontal axis turbines are mostly suitable for commercial applications, like you are most likely going to see them in a large power plant. But vertical axis turbines are mostly used in domestic applications in small scale. For example, they are put on the rooftops of the buildings. Horizontal axis turbines has higher aerodynamic efficiency, but on the contrary, vertical axis turbines has a lower investment cost per megawatt. Manufacturing of horizontal axis turbines are complex. For example, they require yaw control, but vertical axis are simpler. And horizontal axis turbines generate less noise per megawatt compared to vertical axis. So how to simulate rotating geometries in CFD? Ata has explained the sliding mesh or alternating mesh, arbitrary mesh interface technique in detail. And also we have the moving reference frame technique. If we compare them, in the first one, in the sliding mesh interface technique, geometry is physically rotated. But in the moving reference frame technique, governing equations are manipulated, especially the momentum equation. So you can run it in a steady state. But our sliding mesh technique is strictly unsteady, and it requires very small time steps. Non-conforming cell interface require complex treatment, as you can see here. But MRF doesn't have such a numerical problem. SMI is good for highly transient physics, especially for wind turbine simulations, and MRF handles them poorly. It is difficult to set a good initial condition for SMI. It requires many steps until convergence. Again, MRF does not have such a problem. But at the end of the day, SMI is higher fidelity, often used as the primary technique, whereas MRF is mostly used to obtain an initial condition for SMI. Okay, briefly, OpenFOAM is more than a solver. It is a CFD toolbox. So it has mesh generation tools, mesh manipulation tools. It can convert mesh files between another one. It can decompose the domain. It has many useful features, such as, for example, force calculation, field probing already coded in. Many algorithms, schemes, and turbulence models, boundary conditions are already available. Advanced features from cutting-edge research are quickly packed in the new versions, such as dynamic mesh refinement, moving and morphing meshes, synthetic eddy models, and so on. And there are much more to OpenFOAM if you really dive into it. It is open source, it is widely adopted, it is continuously enriched by the active community. A great environment to learn CFD. So in OpenFOAM, you can see the code with your eye. You can run it, you can get a result, then you can modify the code, you can run it again and see how your modification effectively affected the result. It is a finite volume-based code. It is built on incompressible algorithms, in contrary to SU2, which is an compressible solver by heart. So it mainly uses simple and piezo algorithms for pressure velocity coupling. It has MPI-based parallel capability. It has two main branches. Professor Uzol also mentioned this, and Foundation and ESI versions, but they are very similar to each other. You can use any of them. Downside is it has a steep learning curve, so there are no graphical user interface. It requires Linux knowledge, and it may be intimidating to new users. But I would like to show you how this turbulent kinetic energy equation is coded in OpenFOAM. You can see the actual equation here. And on the right-hand side, you can see how it is coded in OpenFOAM. So everything is really very intuitional, as you can see. For example, from the finite volume FVM namespace, you can directly use the DDT function for time derivation, time differentiation of K, and so on. The divergence is div, Laplacian is Laplacian. So you can write your solver, your own solver, as if you were writing the equations by your hand. So what about the moving reference frame? So moving reference frame is a technique that can run in steady state. So it is kind of a difficult thing to grasp. So first you define a rotating axis of rotation. For the MRF zone, within the solution domain, you define a small zone which rotates actually. For each cell in the MRF zone, you define the distance vector Ri of each cell I from its center to the axis of rotation. Then the absolute velocity becomes this one, which includes the rotational effect. Then this U vector is substituted into the Navier-Stokes equation, which generates extra terms. I'm not going to dive into this and explain everything in detail because we don't have time for that. But a single set of equations is solved at the end of the day with rotational source terms added only to the rotating zone cells, as you can see here. U and UR are they appear under the same divergence operation. So it is an uncommon practice in CFD. So this is treated with phase flux correction. The full derivation can be seen in this link. You can check it. Velocity at the boundaries within the rotating frame is corrected also. So if you have some ball boundaries or any other boundaries within the rotating frame, the solid body rotation is satisfied by correcting the velocity at the boundaries. Okay, so let's move on to the simulation demonstration. So I would like to open up my terminal here. Can you see my terminal? Hopefully here.
Yes.
And, so we can connect to the Truba server. Okay, I'm on Linux, by the way, but it doesn't matter. It should be similar in Windows or Mac, I guess. So you can connect to the Truba server using the SSH functionality. My username is Honel, so I'm going to connect to the Levrek1 machine here. I enter my password, and now I'm connected to the Truba server here. I can print my working directory, and you can see I'm in Truba home Honel directory. Okay, I can also mount my Truba home directory to my local machine. How I can do that? I can use sshfs command. I'm not going to write this, but instead I have a function for that. I have Truba mount, or was it mount Truba? Okay, is it mount Truba? I can write mount Truba. I can enter my password. So what I did here is I mounted this directory in the remote machine in Truba to my local directory here. So this is my local terminal. I can go to my home AE Truba directory, and I can list the documents here. So you can see these documents. These documents are actually located in the remote server, but they are mounted on my local server, local machine. So how can you use OpenFOAM in Truba? OpenFOAM is already installed in Truba servers. You can change your directory to here and see the OpenFOAM versions. There are several OpenFOAM versions installed, I guess. OpenFOAM 6, 8, 9. We are going to use OpenFOAM 8 for this demonstration. And also the Truba server uses a Slurm workload management manager. What is does that? It does that. Many people use Truba, right? So everyone submit their job and get into a queue, and this Slurm workload manager manages when everybody's work are going to start or end. So you can get a job script here also. Actually, we can check it. We can go here and let me see. I can write nano Truba SW Santos 7.3 app OpenFOAM and OpenFOAM 8. Oops, sorry, OpenFOAM 8 SPatch. Yeah, you can see the file here. This is located in the remote server. You can write here which queue you are going to use. The Truba has many different queues. You can check them on their website. Your username, your job name, how many cores you are going to reserve, and what is your roll clock time, and stuff like that. And there are many more. Some modules are loaded, some environmental variables are defined for OpenFOAM to work properly, but I'm not going to go into them. You can use this as a template for your JavaScript. And you can go to the okay, let me change directory to my home directory. In your home directory, you have a file named bash profile. So this bash profile file works like that. Whenever you log into Truba, everything written here is automatically executed. For example, whenever I log into Truba, these modules are loaded, C compilers, OpenMPI libraries, and I have some functions, as you can see here. If this OF8 function does everything necessary for OpenFOAM version 8 to work properly. It loads modules, it exports some variables, it defines some paths and stuff like that. I just defined this. So instead of writing them all one by one, I can just write OF8, and everything is loaded from OpenFOAM 8 library. So I can use any OpenFOAM command. For example, block mesh or incompressible solver, icofoam. Anything I can use now, you can see. And finally, we can go to our case directory, which is located in OpenFOAM, Honel 8, and WAV2D. So the good thing about mounting this directory to my local machine, so this is home versus AE. You can see this one. This is my local directory in my local machine. AE Truba. So when I go into Truba, the folder looks empty, but let me refresh this browser by hitting F5, and you can see the files on the Truba server on my local machine. So I can manipulate files easily here. I can open them with my local text editor, and it is very easy to use. Okay, let's move on to our solution, our test case. So we are going to replicate the work from Abdulrahman et al. The solution domain looks like this. We have an outer domain. We have an MRF domain defined here. So there is an interface here. So this frame is going to rotate. It's not going to actually rotate, but this domain will be manipulated to present rotation. And we have three blade sections. So this is a fully 2D simulation, right? So rotor radius, number of blades, the blade profile, NACA 0018, the chord length, pitch angle. You can see the details here. And simulation details are U infinity is 10 meters per second. This is an incompressible simulation. So pressure is, gauge pressure is 0 everywhere in the far field. The turbulent intensity is 10% at the inlet. And we are going to use K epsilon turbulence model so that we can obtain the solution quickly. And K and epsilon values at the inlet boundary is calculated using these functions. At the outlet, zero gradient boundary condition is applied, and at the upper and lower boundaries, symmetry boundary conditions are applied. So they are similar to zero gradient boundary conditions. Okay, so I would like to show you the structure of an OpenFOAM case. So we can go to the WAV2D case using my file browser, local file browser, and we can also see it here. Let me see, where am I? Okay, I'm also here. You can see all clean, all run SPatch, the same files here. Nice. So what does each of these items do? So zero directory, which is not yet which does not yet appear here. It is actually hidden in my stuff directory, which I usually store everything related to not related to me, not going to be used by OpenFOAM yet. So this zero ORIC will be copied into the main working directory later. But let me explain. Zero directory includes all initial conditions for U, P, K, and epsilon, all of the field variables. So we are solving a K epsilon, we are using K epsilon turbulence model, right? So we have U, velocity, pressure, turbulent kinetic energy, anticipation rate field variables. So all initial conditions are defined here. So let us just open one of them. For example, U. So at the inlet, we have a fixed value boundary type, and it has the value of internal field, which is defined here, internal field, uniform, 10 in the X direction, 0 in X, Y, and Z directions. Same goes for P, K, and epsilon. At the outlet, U is defined as 0 gradient. So this is how you define boundary conditions in open form. In the constant directory, we have MRF properties, for example. MRF properties includes what the MRF zone is going to do. For example, it is going to rotate around this origin, around this axis, with this omega value per radians per second. Turbulence properties. It defines the turbulence model. Simulation type is Reynolds average Navier-Stokes equations, and a K epsilon closure model is used. Okay. Transport properties. The fluid is Newtonian, and its kinematic viscosity and density are given here, and so on. In the system directory, you have the control dict. These are dictionaries. Ata explained for SU2, right? So these are the configuration files for OpenFOAM. They are separated into numerous files, unlike SU2. But in the control dict, you can see, I hope these are clearly visible to you. We are going to use the simple form solver. We are going to start from latest time, which is going to be 0. And we are going to stop at end time, which is defined as 50,000 iterations. Delta t is 1. And we are going to print out at every 100 time steps. And you can define custom functions here. For example, I'm going to use y plus function, which will print the y plus value, which is going to calculate y plus values and going to print them. So I load necessary libraries for that and write down the necessary definitions here. And also I'm going to calculate forces, because at the end of the day, we are interested in forces, right? What is the moment, torque? What is the forces in x and y directions, drag, for example. So I define rho infinity as 1.225 because we are simulating air. You have to define this because in OpenFOAM's incompressible solver solves equations per density. So it solves equations independent of density. And center of rotation is defined here. Okay. Let's move on to, for example, decompose pardict. This defines how the solution domain is going to decompose. So we have our solution domain here, right? So it is going to divide this solution domain into simply 4 domains, 2 in the x direction, vertical, and 2 in the y direction. So we are going to obtain 4 domains at the end of the day. Okay. And FV schemes and FV solutions, solution files. These are very important. FV solution defines which algorithm you are going to use to solve pressure equation, to solve velocity equations, K equation. And also you define the convergence control here. For example, our solution will converge when the residuals drop down to 10 to minus 6. And you also define relaxation factors here, which is necessary for simple algorithm to work. A simple algorithm works with relaxation. So if your simulation is diverging, you may try lowering these values. This doesn't affect the final solution, but it affects how you reach the final solution. Lowering these values will make your solution more stable, but it will take more time to finish. Okay, what else? Polymesh. We don't have the Polymesh file yet. It is again hidden in my stuff directory here. It includes all the mesh, it includes the mesh file, the solution grid, and necessary definitions here. There is too much to talk about, so I'm going to skip, but the boundary, phase data, cell neighbor data is all stored here. So I've generated the mesh beforehand. I'm going to show you the mesh. It's all here. And this all-run S-batch we are going to, this is the file we are going to submit to the Slurm workload manager, right? So the Slurm workload manager will check these parameters, and it is going to submit, it is going to get this job to the mid2 queue with these parameters, and it's going to execute the job. So what do we have here? Account Honel. This is my account name. This is the job name, about 2D. We don't have reservation. This is unnecessary here. Okay. So we are going to get four cores for our parallel simulation, which is consistent with our decompose par definition. We are going to partition the domain into 4 subdomains. We are requesting 1 hour of wall clock time. It is even, we don't even need that much time. It's going to finish quickly. If you want, if your job takes too long, you can ask Slurm to send you an email when your job is done. You can define your email here. And everything, every output will be written in the Slurm out, and every error will be written to the Slurm error file here. Not here, but here. Okay. So as I mentioned, first I source the job manager will source my home, my bash profile. It will load every module necessary, and it will load the environmental variables for OpenFOAM using this function. If you remember, this function is defined in my bash profile file. So it will load some necessary run functions from OpenFOAM libraries. For example, by loading this, you can use run application and run parallel functions to run your OpenFOAM applications. Okay, so this 2-line will simply copy my stuff 0 oric, this file, into the case directory as 0. So this will just copy this directory and paste it to the case directory as 0. And similarly, it's going to copy my mesh as polymesh into constant. And it is going to first decompose the domain using decompose par application. Then it is going to run application in parallel. So what is application? This is a feature of OpenFOAM. Oops, sorry. So this run parallel application will go to, will go to system. It is going to check system control dict, and it will get this application, and it will see the OpenFOAM text here, and it is going to run OpenFOAM. So if you change your application from simple form to pimple form, for example, it will automatically run pimple form. Okay, so I guess everything is clear. So let's move on to running our simulation. I hope we have time for that. Okay, so let me first see where I am. Print working directory. So I'm located in the correct directory, Vault2D. So what I have to do is I've made everything ready beforehand. I will just submit my job to the Slurm workload manager. For that, I can use sbatch, all run sbatch. So this will effectively submit all run sbatch file. Let's hit enter. Submitted batch job with this ID. So you can see how is your job is doing in the queue. For that, you can execute the sq command. Okay, so it says it is running. R means running. It is running in the Barbun 48 node list. Okay, so if I refresh my local file manager F5, you can see that some stuff is going on here. First, First of all, the decomposed par application of OpenFOAM has divided the domain into 4 subdomains. Each one is stored in processor 0, 1, 2, 3. And it also writes the functions I have defined in control dict, which are y plus, forces, and residuals functions into post-processing. You can see here, forces are written here, residuals are written here, and y plus is written here. So using the let me clear this. Using the form monitor application of OpenFOAM in log scale, I can plot the residuals live. How can I do that? Oh, sorry. First, I have to change my directory to OpenFOAM Honel 8 and WA, this working directory. Now I can use form monitor in logarithmic scale, show me the residuals. Yeah, so you can see here how our residuals are converging, right? So if we wait for some few seconds, you are going to see that this graph is updating itself every 5 or 10 seconds, I guess. So you can see here that residuals for P, velocity, K, and epsilon are dropping. And they are going to keep dropping until the convergence criteria is reached. So what is our convergence criteria? It is defined in the FE solution file. It is 10 to minus 6. So there's a good thing with OpenFOAM. We can change these values on the fly, and OpenFOAM is going to accept the changes. So if I change this convergence criteria to 10 to minus 5 and I save this file, solution will most likely stop because 10 to minus 5 is already satisfied. So let me save this file and let me check the job queue. You see, the job is terminated because OpenFOAM, the simple form solver checks FE solution file at every time step and checks for any changes in this file. If there are any changes in this file, it is immediately reflected into the solution. So this is provided by this definition in control dict. Let me see it. Let me find it. Runtime modifiable. If you make this true, what I've explained works. If you make this false, it doesn't check anything during runtime. So whatever settings you have defined at the beginning persists throughout the simulation. Okay, so we have a solution, right? So we can check the solution by using ParaView, which Ezgi has explained in detail previously. I have a state ready here. What is a state? I have saved my ParaView screen to show you previously. I'm just going to load this. Okay. So this loading is most likely, it is going to take some time because actually my local machine is getting data from the Truba servers right now in the background. This is why it takes some time. Okay, I hope everything will work fine. Okay, let me go to the final time step, to the final frame. So this is our final, oops. This is our final solution frame. You can see here that the streamlines are deflected due to the rotation of this frame, MRF zone. Actually, I can show you the MRF zone like this. So this is our solution domain. This is the inlet on the left, outlet on the right. We have this MRF zone. If you can see it, there is a circle, there is a fine circle here. So all of the cells within this domain, within this zone rotates. It doesn't rotate, but it simulates rotation. And we have our airfoils here with boundary layer mesh around them. And you can change this color to U to see the solution. Okay, so we have a solution. And what else we can do? We can check the forces, right? So I can go into forces. How I can do that? Go to post-processing, forces dot. Okay, so is this visible? Hopefully this is visible. So it writes forces, pressure, viscous, porous, and moments, pressure, viscous, porous, like that. So this part, yes, this part contains forces. So this is the X, this is the force in the X direction caused by pressure effects, Y direction caused by pressure effects, and Z direction caused by pressure effects. So Z direction is effectively 0. 10 to minus 19 means 0 actually, because this is a 2D simulation. And similarly, viscous and porous. Porous, we don't have some porosity in our simulation. So it is 0. And similarly, moments. You can see the moments here. So let's just go down to the converged time step. In the final time step, in the final iteration actually, we have so we are interested in the moment around the Z direction, right? So we are interested in the last component of the moments, this one and this one. Actually, if you check moment around X and Y directions are effectively 0 again, 10 to minus 18. So these two values are the ones we are interested in. This one is caused by the pressure effects. This one is caused by the viscous effects. But at the end of the day, we are interested in summation of these two, right? So I have written a simple MATLAB script. I will going to run it in Octave, actually. Let me see. Let's go to my stuff. Okay. So, oops, sorry. Can you see this? Hopefully.
Yes.
Okay, so this just calculates the power coefficient. I'm not going to explain it in detail. I'm going to go into my stuff directory and I'm going to run Octave, and this pressure and viscous forces, we can get these from also we can get this from log simple form. Okay, sorry, we can't get them. Okay, from here, we can just copy these values. There are more elegant ways to do that actually, but let's just do it quickly. So these two are the momentum pressure and momentum viscous. So we are going to sum them up and calculate the CP. I will just run power. So tip speed ratio is 2, and our power coefficient turns out to be 0.28. So let's compare this to the reference value. Let's discuss the results. So the paper from Abdul Rahman finds the reference value, finds the CP by 0.29. In my previous run, I have found it as 0.25, but now that I have allowed to residuals to drop further down, the relative error is even less, right? So we are very close to the reference value. But these results does not mean these results are true. So there are some questions to ask here. First, does multiple reference frame really reflect the physics of the problem? It is worth checking the method's sensitivity to radius of the rotating zone. So the radius of the rotating zone is defined as that. But what happens if this is smaller or larger? This could be investigated. And also position of the turbine. What if we didn't put this plate here but here? What if we rotated this turbine geometry by 30 angles, for example? Are we going to get the same result? This could be checked. How well do the K epsilon model and its wall functions work? So we should also check the y plus value. So the first cell should be located here when you are using a wall function, right? The fully turbulent log law zone. So we can also check the y plus value. We can go to post-processing, y plus 1. And we can check as you can see, the minimum y plus value in our simulation around the walls is 16 and the maximum is 80. But we know that putting your first cell well below the viscous sublayer or within the buffer zone would yield erroneous results, right? So the first cell should be here, around here. So what we did was a not good practice, but this is just for demonstration purposes. So this should be also checked. Is the mesh good enough? We didn't check the grid convergence. And also we have only used first order schemes in this simulation. You remember the FV, too many things on my screen. Let me check this. Yeah, in the system directory, FV schemes, these are the schemes we have used for divergence, gradients, and stuff like that. So Gauss upwind is a first order scheme. It is very stable. It converges really fast. I've used this for demonstration purposes, but this doesn't yield correct results. The results in ParaView may look correct, but actually it is not. So these should be checked. And finally, the simulation should be run at different tip speed ratios also. We are just on time, I guess. Thank you for your attention and hope you have learned something new.
Yes, thank you, Seyin. Very good job. Right on time again. Thank you. Actually, I had a question. You showed the residual plot. You run it on your mounted
Yes.
directory, and how did it work? I mean, we saw the GUI. So is it working on your computer or on Truba?
Hocam, it runs on my computer because as far as I know, Truba doesn't have an X server, so you cannot get visuals from Truba. I might be wrong, but I couldn't manage
Yeah,
that.
you need to open the X server to be able to see the GUIs from Truba. If you didn't do that, yeah, but when you run,
if you run form monitor in Truba, if you were able to do that, Truba will just send you the visual. It will just send you the visual only. But if I run it on my local machine, it will load the data, load the raw data from Truba server in the background. You don't see it, and render the image on my local machine. So the thing is, if this Y plus data is just 4.1 kilobytes, but if this were, for example, 1 gigabyte, if this was 1 gigabyte in size,
yeah,
it will take a
time.
much longer time. Yes.
Yeah. So when you monitor that function,
Hocam, this function,
I mean, is it on your system? Does it see your system? So which
it is on
function?
my system. It is on my system. I'm using I'm using the OpenFOAM installed on my. Actually,
Also.
I have opened this using OpenFOAM 9 because I have OpenFOAM
Okay,
9 on
yeah,
my
that
system.
was my question. Okay.
Yeah. And I was running OpenFOAM 8 on Truba, but uh,
It should give the
thankfully,
same. Yeah.
yes, thankfully we don't have much version differences between these two, so it is easy
Okay,
to just open.
great. Thank you.
You're welcome.
I don't know if any other questions we have. Okay, maybe I can also ask, did you check the scalability for OpenFOAM? I mean, maybe we should, we can make a comparison of SU2 and OpenFOAM using the same grids on Truba to compare the performances of the codes. I think there is one,
Yes.
that was one question. Yeah.
Hocam, actually, I have an idea of comparing SU2 and OpenFOAM in terms of both scalability and Ata has mentioned the compressibility effect, right? The tip
Yes.
reaches Mach 0.2. This is very interesting because I would also like to see how the results,
Yeah.
what results do we obtain using an incompressible solver and a compressible solver. That would be an interesting case to observe.
Yeah.
Maybe
Yeah.
Ata and I
You
may
can, yeah.
run the same simulation with SU2 and OpenFOAM, maybe.
Yeah, that's a good idea. Thank you. We will do that, hopefully.
Okay, hocam.
Okay. If you have, attendees, if you have any more questions, you can always, always ask later on also. So you can reach us anytime.
I had to rush a little bit because there are so many things to talk
Yeah,
about
sure.
from zero to simulation on Truba, but
I
I've
think you covered
skipped.
very well. Yeah,
Thanks, hocam.
it was very clear, and it will help for the beginners and for the advanced students as well. They can, if they
Hopefully,
already know, they can apply this test case easily. Hopefully, we will provide the sample files so you can try by yourself.
sure.
Yeah, great. Thank you very much.
You're welcome.
So I think we have a break now, and then we will start at 15:30. So we can have 10 minutes break, have coffees and teas. If you are hungry, you can grab some things to eat.
Hocam, beraber içmek çok güzel olurdu şimdi
Evet,
kahvede.
maybe next time we should try this face to face also. It will be more fun, of course. Maybe we can arrange a session like that, for if anyone wants to have or able to come. We can also make a short session, face-to-face session in the future for more discussions. Okay, thank you. See you after the break. So we will meet at 15:30.